All right, thanks so much for inviting me, Lucas, and let's get right into it so we don't waste too much time. If you're joining other talks this week, I'm sure you'll see something at the beginning about replication or replication crisis. So here's my 2 cents. This is from many of the slides, in addition to this one, are from a paper about teaching replication that was published with some colleagues in 2023, and it shows articles that discuss or refer to the replication crisis by year and discipline. And you can see that around 2015, things really take off, and psychology has the largest amount of articles. Um, what is replication? We were just talking before the talk about how there's a lot of different ways of thinking about this, but maybe a really general definition to just kick us off for this particular talk, in case you haven't joined any of the other talks, is the idea that scientific knowledge, including social science, depends on generalizability in a lot of ways, or this is one key form of knowledge, and the goal is to establish some general truths within certain scope conditions, of course. This is really important. And the development of these so-called truths comes from testing and retesting. And retesting, of course, is replication. The replicator uses some previous knowledge from some previous test and designs a current study, and replication is a well-established scientific method. Replication is just science. I'll post these slides in Zenodo. We also just talked about that. They're not there yet, but they'll be there soon. And you can follow that link to find a huge list of different definitions of replication. But there's two really important features. One is it the same data or not? And one is it the same methods or not? And here today, we're talking about computational reproduction, which is supposed to be the same data and the same methods, ideally even the same code, if that's available. Now, that's called verification in the scheme I just showed you. There's a lot of different names for it, but a computational reproduction is much more than just a verification. By doing computational reproductions, we can foster a change in scientific norms and build open science practices. By doing these computational reproductions, the whole idea is to reproduce something. So we need to identify the thing, we need to look at the materials we have, and of course, our computational reproductions themselves should be reproducible. So it's an entire open science way of life. And what it also does with computational reproductions is it gives us a link or an opportunity to engage with other scientists and maybe avoid this silo problem where a lot of science or scientists are operating in a so-called silo where they sort of only communicate with themselves or a small group of people. And sometimes a computational reproduction can be a way to link across disciplines or subfields or something like that. My experience with computational reproductions is beyond verification, invariably we learn something new or several new things. I'm going to talk more about that. Another reason why computational reproductions are really important is we have tons of studies out there now looking at computational reproducibility and open science and things like that. And from all the studies that I've seen, between 25 and 75% of published statistics are not reproducible within some sort of defined metric. And based on some surveys, between 18 and 40% of active researchers openly share their materials like code, data, and workflow. That means the majority of researchers are not actively sharing their materials in the social and behavioral sciences. Another reason we've seen evidence that different software and even different versions of the same software can produce different results when we're using the same code, for example, or we think we're using the same methods. There's a really cool program, we'll call it a program or app called StatCheck. And using this, different scholars are able to check p-values in studies, publish papers, usually using some kind of null hypothesis significance testing. And it's a really cool tool. There are some criticisms of it, and it may have some inaccuracies, but about half the studies have like at least one statistic that doesn't match. So you have p-value, you have degrees of freedom, you have something among these statistics seems to be inconsistent, and therefore could I be identifying an error. There's a lot of benefits of doing computational reproductions for especially newer, younger students, like bachelor students, for example. It would be a chance to develop methodological competence. Probably if they do a computational reproduction, they're going to be doing something they never done before, not just a reproduction, but a method. So maybe they've never run this type of regression model or, whatever the statistical test is. And it's a way to do learning by doing. And also, in a computational reproduction, we have to really focus and critically evaluate the research that was done in order to understand it. And this is a especially important skill for a scientific career or doing science. For graduate students, it's a way to really get integrated into the scientific world and definitely a way to advance a career, especially today in the post-open science movement world. Um, replication is a way to get into a theme. When you're doing a dissertation, for example, there's always those key publications on your topic, and it's like, hey, you can go and computationally reproduce them. And in doing so, you might network with the original authors and have some exchange. And it does create an opportunity for presentations or even possibly a publication. Now, for career scholars or those teaching, it's a way to refresh skills or upskill. A lot of us that are like my age and especially older didn't have like themes of open science. They didn't learn to do reproducible research from the beginning. And so this is a way, by doing computational reproductions, it's really frustrating to try to reproduce work sometimes. And it's a way to realize, oh my gosh, if if it's so frustrating for me, it's so frustrating for others to reproduce my work, and I can learn about the value of being more reproducible in my work. This is also from our paper, which is about teaching with computational reproductions, and it's like a rough timeline, what you might do in a course, but we put together the concept of a semester-long course, and so a semester is, as it turns out, it's a good time frame for trying to conduct a computational reproduction, especially if you're following all these steps. If you haven't yet chosen a study, you need to also track down the data and code, older studies. You're not going to find this stuff usually online. You might have to contact the original authors, or you might have to create your own code to do it. So this is just like a conceptual thing for you. Big question in computational reproductions is, what is a successful computational reproduction? And there really is no standard definition. I think one of the most important criteria, based on my own experience, is to look at the original conclusion. You have some original study you want to computationally reproduce. What was the conclusion based on? So was it an effect size? Are they saying, hey, there's a big effect of something on something? Was it based on a threshold cutoff, maybe null hypothesis significance testing? Was it based on something else? Was it a simulation, like this is what we expect in the population, item response theory? I don't know. There's a lot of different things. And so if you base it on the conclusion, I mean, the important thing in the science of knowledge production is that it would be the same conclusion if you reproduce the results. But a real basic way of doing it is having like the same direction and the same sort of significance if it's in that null hypothesis significance testing world, or something like the same numerical effect. A lot of these studies use a decimal place. Okay, if it's rounded to the second decimal place, or if it's within 5% or 10% of the original, or if there's some kind of credible interval or posterior distribution that matches roughly to the original. Some have suggested matching precision to the original paper. So if the original paper reports 3 decimal places, then the reproduction should match 3 decimal places. But spoiler alert, all of the research we know of tends to not reproduce it. There's too many little things that can enter the process, like you use an Excel file from the data and it gets rounded somewhere in the process. And so 3 decimal places is really was really unlikely to get exact to 3 decimal places. Possible, but unlikely. Okay. So it's important to have a reproducible workflow. I'm just going to kind of jump ahead a little bit. Reproducible is really nice if it all fits into one folder, and you can, zip this folder and pass it on to other people. You can synchronize this folder in a repository. So it's nice to have a project folder. It's really the ideal way of organizing it rather than, oh, I have some stuff here on my computer and some stuff here, and you get a link online. And this is just like one example. And if you have steps in the research process, it's nice to number them so that the user can kind of get a sense of the order of things. And especially in the syntax folder, those of you that are really young, maybe you haven't heard this word, but code, it's nice to number the code so that you can see like, run this code first, run this code second. It's very helpful. You want to be able to save, synchronize, and share your work. There's tons of tools out there for this. I forgot my laptop on an airplane, and I went back and it was gone, and no one could find it, and it was just gone. And that was sad. It was a work laptop. I got a new one from work, luckily, and I didn't miss a beat. It was such a, it was, I really saw the value of open science and reproducible work because it was just like, well, I just resynchronized all my projects, Of course, I had to reinstall the software and stuff, but everything was stored somewhere in a cloud. Everything was synchronized, and I could just keep right on going. And so I highly recommend that. I'm not going to recommend any specific tools today. There are so many. We can talk more about that if you really want to in the Q&A. One of the most important things about a reproducible workflow is literate coding. This is something I didn't used to do. I used to just like have a code file, and I myself can't reproduce my own research from the early parts of my career because I look at it and I'm like, what was I thinking here? What was I doing? This is crazy. It's so unorganized. And so literate coding is a concept where you want to make lots of detailed notes every step. It's like, here I'm doing this and this and that. And and in Stata, this would mean like comments. You have the little asterisks or this thing that you can put it at the end of the code line. Also important for reproducible workflow is version control. And this in Stata, for example, is really easy, right? You just type the version number. You have to make sure you have the correct ADUs in there. And it's really good to use things like do files, globals, log files, output files. These are all really helpful because sometimes a user may try to run your code and they don't get the same results and they want to see. And so if you have a log file, they can see what happened when you ran your code, and maybe it's easier for them to debug. It's the same with R, literate coding, comments, literate coding, literate coding, literate coding. R has R Markdown, which can be in any IDE, of course, and can be really useful. There is a way to do a Stata Markdown. R is a little bit more flexible in terms of using different IDEs, but this is really important for me. I would say, especially for students, younger researchers who have never used R, they should really carefully consider if it's necessary. R requires a certain degree of data science work, which means lots of troubleshooting. And if this kind of work is just not something you want to get involved in, maybe Stata is better. It just runs out of the box. R does support more of the open science, right? It's open source, but think carefully about, I don't just automatically recommend, oh, everyone should use R. And if you're using machine learning, for example, you might rather use Python. So just a little bit of caution there. Version control is really important. It can be a little trickier with R. There are, of course, many benefits to using R. We don't need to talk about those. That's not the point of this talk. There's lots of other software, obviously, out there, but this is a really important question about computational reproductions. Do we need to use the same software as the original authors? Well, if we don't know how to use the same software as the original authors, this could be challenging. I don't know the answer to this question, but we did do a study recently where we had replicators, we had the crowdsourced replication initiative, And people were reproducing an original study, one half of it were it was an experimental assignment. They got no code from the original authors. They were just given a description of the methods. The original authors did the study in Stata, and those who used Stata got more often got the same results or closer results. And this signals something very idiosyncratic about software. There's something native about software that may, the packages or the way it's designed or the way the people are that use it that may lead to different results. And so I just want to raise awareness of that. However, at the same time, we might be able to learn something new if, for example, the original was done in Stata and I come in and do it in R, maybe I get different results, but it can help teach me something about why. This is especially true for more complicated models. For OLS regressions, I don't expect to get different results in any software, for example, but this relates more to more complicated models. You want to make some kind of replication package. There's a lot of links in this in the paper where a lot of these slides came from and here in the slides. And here's like a list of things to just think about. Do I have these things in my replication package? I've been using GitHub, for example, and I always have to kind of like kick myself to like, hey, make the README, make a nice README for other people to be able to figure out where to start and what to do. Because, I'm just running my code and this and this and that. And then when I want to share it, I always have to remember, I need to think from the user's perspective, not just from me trying to achieve the research goals. There's also some templates you can use. There's links in there. Okay, well, something we're going to do in computational replications is to look for coding errors. Why do we look for coding errors? Because this would be the most obvious reason that you came to different results than the original study, right? That there's some kind of error in the code. They made some mistake so that what they reported is not actually what's in the code or vice versa. So you want to look for those kinds of errors. Are these the exact same files? Are these the exact same data files? What about treatment of missing values? Is the statistical model really what is reported? I know that a lot of people, and I think I'm guilty of this too. I've run the code, I've gotten my models, and then I go back and edit the code because I want it to look nicer or reorganize it, but then I don't run it again. And yeah, that's dangerous. Okay, next big question. Being stuck with this publish or perish norm, which we should try to get rid of course, but it's still there. Should every computational reproduction seek publication? I would say online, yes, but that just means it should be posted somewhere online. If you do all this work to computationally reproduce something, put it somewhere that the other scientists, the public can find it. That's very valuable, especially today as we try to shift a little bit away from this old traditional way of doing science. It isn't necessarily going to be in a journal, though. Just be aware. So if you invest a lot of time in computational reproduction, just be aware if you're just hell-bent on publish or perish, this may or may not be the direction you're going. And the reason is that if you have a successful verification, so you figure out how to redo their whole analysis, maybe it takes you a really long time because they don't share their code, and you're like, yes, the original authors, I can reproduce their results. This is not going to be published. I'm sorry to say, it's just not something that a journal says, oh, great, let's make an article out of this, which is sad because that is so valuable to science knowing that we can rely on, this is a statement or this is evidence that, hey, what they did is reliable. The what they reported, it works, it runs. Those results, they're not somehow a mistake or, they moved a decimal place around or they changed the p-value just to get published or something. Sadly. If you do find errors and you can issue a correction, this could be a publication, but it depends on what's corrected. It depends on how big it is, unfortunately. This is really a question of how sexy are the results. That brings us to a concept which, if you do a computational reproduction and you're, critically evaluating the paper, a lot of times it could motivate an extension where you say, oh, now that I've done this, it actually makes sense to me, based on some theory I'm familiar with or whatever else, to extend the study. And this is where you definitely could get a publication. And it brings up a question because most research with statistics throughout the history of science is some kind of extension. It's taken some previous research and extended it. It's just not framed as a replication. So then this really difficult question comes up. Do we have a title like, an extension of, authors X and Y to 2023? Or do we just write something new? Because it seems like still today, many journals are more interested in studies that frame things like something new, like here's a new study about this topic. But a more honest and better way of doing the scientific method is to be like, hey, I'm replicating this result and extending it. So it's just something to think about. Coming up to the end of the talk, extending a study. Why would you extend a study? There's different reasons. I think number one is theory. Like if there's different causal theories, different data generating theories to work with, and you're looking at the study and you're like, gosh, why didn't they include education in the variables? Like we know so much about education's effect on this outcome. But another reason, which isn't necessarily have anything to do with theory other than to maybe confirm something, is robustness checking. And this is really important, if you think in the social and behavioral sciences, we normally don't know the data generating model. It's really complicated, right? It's really, really complicated. And so there's all these different plausible ways of doing things. There was a talk yesterday about the multiverse analysis. And this would be a way we could extend it in different ways and check the robustness. Also, if you're a student doing a dissertation, maybe there's like 4 studies that are really important in your area, and they're all kind of using the same data, but doing a slightly different thing. And you want to kind of combine them. So you could say like, here's like 4 different plausible models plus some extension. Unfortunately, there's a lot of people who replicate with the intention of taking down a study and showing that it's wrong. And I don't know that this is a good reason to do things because it opens up the possibility of hacking where you could say like, oh, if I define a successful verification at 0.05 or zero 0.1, then they're wrong. Then their results are not replicable or verifiable. And if you have that goal, then you're like, you're hacking the criteria or the thresholds. And there's a lot of egos in science. Check your ego. Maybe that's not the good reason to do it. So thanks for your attention. I look forward to the discussion.